The isomerization of methyl isonitrile to acetonitrile was studied in the gas phase at 215 degrees Celsius. The following data is obtained, right? So at time 0, we have a certain concentration. After 2,000 seconds, the concentration goes down. 5,000, it goes down, down, down. Okay. Calculate the average rate of reaction in moles per liter second for each time interval. All right, so that's part A. So that's change in concentration over change in time. So for the first 2,000 seconds, I went from 0.0156 mole per liter to 0.011 mole per liter. And I get the change in concentration divided by the change in time, and I get the rate. I get the change in concentration over the change in time between 2,000 and 5,000 seconds. That's a difference, or that's a change of 3,000 seconds. Divide that in the change of concentration, I get the rate. And I get the rate. And I get the rate. And I get the rate. So those are the changes in concentration over time for those time intervals. If I plot those, difference between the initial concentration and the concentration after 2,000 seconds, right? That's the points on the line. The slope of the line is equal to the rate. So this is the slope of the line at the beginning of the reaction, right? After the first 2,000 seconds. After the next 3,000 seconds, this is the slope of the line. And this is the next slope of the line after the next 3,000 seconds. And then the next 4,000 seconds, that was the slope of the line. And the next 3,000 seconds, this was the slope of the line. So slope of the line is the same thing as the rate when you plot concentration versus time. So we can see that, hey, as the concentration of this compound goes down, the rate's getting slower. So the concentration of this compound has an effect on the rate of reaction. B, calculate the average rate of reaction over the entire time from t is equal to 0 to t is equal to 15,000 seconds. All right, so change in concentration over the 15,000 seconds. I take my initial concentration, my final concentration, get the difference between them, and I get the slope of the line over the entire time interval. So that's this line. So you can see that this line isn't as useful as having small increments of time, right? It's not really valuable, right? At the beginning, we had a much steeper slope than we had at the end, so this doesn't really give me the information I want. The most powerful thing is to know what the slope of the line is at any point on this curve. And to do that, we have to use calculus. We have to derive. A derivative is the slope of a point on a curve. So when I take the derivative of the point 5,000 seconds, I get an instantaneous rate. The slope of the line perpendicular to that point on the curve at that point. So that is the instantaneous. If I want to know what is the concentration at 5,000 seconds, or what is the rate of reaction when the concentration has changed after 5,000 seconds, I can get that by taking the derivative. At 8,000 seconds, I get an instantaneous rate. What is the rate of reaction at 8,000 seconds? So that's the power of calculus. Now, this is a non-calculus course. We don't have to derive here. But what you do have to know is what the difference between instantaneous rate and average rate, right? Difference between 2 points on the curve as opposed to the slope of the line perpendicular to a point on the curve. Instantaneous rate's more useful. All right, 26. Consider the combustion of ethene turning into carbon dioxide and water. If the concentration of ethene is decreasing at a rate of 0.036 mole per liter seconds, what are the rates of change in concentrations of the carbon dioxide in the water? All right, so this is relative rate. If I know what the rate of the disappearance of ethene is, I can use the coefficients in the equation to equate how fast CO2 is appearing and how fast water is appearing, all right, by using the coefficients. So both carbon dioxide and water are appearing twice as fast as ethene is disappearing. B, the rate of decrease of N2H4, the partial pressure in a closed reaction vessel from the reaction with hydrogen to form ammonia, is 74 torr per hour. Right, so we've got a pressure change per hour here. What are the rates of change of ammonia partial pressure and the total pressure in the vessel? All right, so according to the balanced equation, for every 1 mole of N2H4 disappearing, 2 moles of ammonia are appearing. All right, so the rate of the disappearance of N2H4 is half as fast as the appearance of ammonia. As far as the pressure in the vessel goes, I'm losing 2 atmospheres of gas on the reactant side and making 2 atmospheres of gas on the other side. So the pressure in the container isn't changing. All right, for every 2 atmospheres lost in the reactants, I'm making 2 atmospheres, or making two pressures, I should say. We're not using atmospheres. We're using torr in the products. The iodide ion reacts with hypochlorite in the following way. This rapid reaction gives the following data. Okay, write the rate law for this reaction. All right, so this is how we find rate law, right? What effect the concentration has on the rate of reaction. We compare different experiments. So we have experiment 1, 2, and 3. In experiment 1, we have certain concentrations of the reactants, and we see what the rate is. And then we compare it to another experiment where we change the concentration of the reactants. So if you're looking at experiments, difference between experiments 1 and 2, we're tripling the concentration of hypochlorite and holding the concentration of iodide constant. We want to see what effect hypochlorite has in the rate of reaction. Well, it changes it. So what we do is we look to see what the change in concentration is, right? We double the concentration, and then we divide the small rate into the big rate to see what effect it had on the rate. Well, doubling the concentration, double the rate. So this tells me it's a direct relationship with respect to hypochlorite. So that's a first order relationship. All right, then we look at another set of experiments to determine what the effect iodide is having on the rate of reaction. So if we compare experiments 1 and 3, we're holding the concentration of hypochlorite constant, and we're doubling the concentration of iodide. And again, it doubles the rate. So this tells us that it's first order with respect to iodide. So this is a second order rate law overall, meaning if I double the concentration of both the reactants, I'd be going quadruply as faster, right? I'd have an exponential effect. So a direct relationship with respect to both reactants. All right, B, calculate the rate constant with the proper units. All right, the way we do this is now that we've figured out what the rate law is, I pick an experiment, and I don't know, I always pick the first experiment just for choice. I take the data, I plug it into the rate law, all right? So with these concentrations of hypochlorite and iodide, I have a certain rate. It's going 1.36 times 10 to the minus 4 moles per liter seconds. So in order to get what the rate constant is, I divide both sides by the concentrations of hypochlorite and iodide and get K by itself and figure out what the K value is. All right, so we divide moles per liter second, that's the rate, by moles per liter. Moles per liter cancels, and then if I divide by moles per liter again, I get liter seconds per mole. All right, so that's the unit for K for a second order rate law. C, calculate the rate when we have these new concentrations. All right, so now that I know what the rate constant is, I can just take these concentrations, plug them into the rate law, and know what the rate is. I mean, this is the power of knowing what the rate law is. I can plug any concentrations into this now with the rate constant and figure out what the rate would be with these concentrations. So how fast is this reaction going, in my patient's body with these concentrations of drugs, right? So if it's a second order relationship, I can plug in and solve for what the rate would be with these concentrations. So this is rate law. We get it by looking at experiments, changing the concentrations and seeing what effect it has on the rate. The reaction between chlorine dioxide and hydroxide to form chlorite, and water was studied with the following results. All right, so we had 3 experiments with different concentrations, different rates. A, determine the rate law for the reaction. All right. So if I compare experiments 1 and 2, I hold the concentration of hydroxide constant. I triple the concentration of chlorine dioxide, and that has a 9-fold effect on the rate. All right, so this is a second order relationship with chlorine dioxide. Tripling the concentration exponentially increases the rate. So second order with respect to chlorine dioxide. If I compare experiments 2 and 3, I'm holding the concentration of chlorine dioxide constant. I'm tripling the concentration of hydroxide, and that triples the rate. All right, so first order with respect to hydroxide. So this is a third order rate law. Tripling the concentration of chlorine dioxide quadruples the rate. If I was doubling the concentration of hydroxide at the same time, I'd have to the third power faster. All right, have an 8-fold effect. All right, so calculate the rate constant with the proper units. So pick an experiment. I don't know. I always pick the first one. Rearrange the rate law to solve for K. So plug in the rate. Plug in the concentrations of chlorine dioxide and hydroxide in experiment 1. And we solve for K. All right, so the unit for a third order rate law is L square, liters squared divided by moles squared per second. C. Calculate the rate when I have a 0.1 molar concentration of chlorine dioxide and a 0.05 molar concentration of hydroxide. So when I plug these concentrations in along with the calculated rate constant, we can solve for what the rate would be with these concentrations. Again, the power of the rate law. We can solve for what the rate would be without having to do the experiment. We just plug into the rate law. Sketch a graph for the generic first order reaction of A turning into B that has the concentration of A on the vertical axis and time on the horizontal axis. All right, so guys, if it's a first order relationship, that means as the concentration of A changes, the slope of the line changes. So we get a curve. So is this graph linear? No, it's a curve. As the concentration goes down, the reaction rate slows down. B, indicate on your graph the half-life of this reaction. All right, half-life is defined as how much time has to go by in order to halve the concentration. So if I call this concentration on this line 1 molar, how much time has to go by to halve that 1 molar concentration? All right, so at this particular, with this particular concentration, I touch the line here at this particular time. When I halve the concentration, we now touch the line, touch the curve at this point on time. So the difference between the 1 molar concentration and the 0.5 molar concentration is half-life. How much time had to go by to halve the concentration?